Hello everyone and welcome back to tutorial 7 of MIE100, the dynamics course at the University of Toronto. Today we're going to be solving problems on plane kinematics of rigid bodies, specifically rotation. For our first problem, we've got a mechanism shown that rotates about the vertical axis with an initial angular velocity of 2 seconds. And initially, the two masses are in a horizontal plane, and a hinging system internal to the mechanism then lowers the two masses to 30 degrees from the horizontal plane. The masses are each 600 grams, and the original distance of each mass from the rotating axis is 200 millimeters. So, first of all, if the mechanism is freely spinning, so there's no friction, what is the angular velocity of the mechanism after the masses are lowered? And B, we also want to know if the motor on the shaft is turned on for 3 seconds and returns the rotational speed of the shaft again to 2 seconds. When the masses stay in the dash configuration, what is the average moment supplied? And finally, we want to find out how much work is done by the motor. So for this question, we're going to first write down what we know. So we know our initial angular velocity, which is 2 per second at theta equals to 0 degrees. And then for our second configuration, theta 2 is at 30 degrees. We also know the masses are equal to 600 grams. And the distance between the mass to the middle is basically 200 millimeters or 0.2 meters. For part A, we want to find the angular velocity after the masses are lowered. To do that, we're going to do conservation of angular momentum. So we know that our sum of moments at 1 is equal to our sum of moments at 2. We have two masses in the beginning, so 2 mv1d is going to be equal to 2 mv2 d cosine theta 2, because now it's at an angle of theta. Now we're going to substitute our v's with our curvilinear, using our curvilinear kinematics. So we know that v is equal to r theta dot. So we're just going to substitute our v with r theta dot, so it becomes 2m d squared theta dot 1, because r is equal to d for us for part 1. And for part 2, it's d cosine theta. So it becomes 2md squared cosine squared theta 2 multiplied by theta dot 2. Most of these things are going to cancel out. And we're left with theta dot 1 is equal to theta dot 2 cosine squared theta. We're going to plug in our known values to get a final answer for the angular velocity of 2.67 per second. Now for part B, the motor is going to be turned on for 3 seconds, and the angular velocity becomes equals to 2 per second. And the configuration of our system is going to be the same, so they're going to be exactly at the same spot now. So our r is going to be, again, d cosine theta 2, which is the same as r2. Our r1 is the same, it's going to be d. And we want to find the average moment. So I'm just going to draw a simple free body diagram to understand what's going on. So at t is equal to t2, it's equal to 0. So that's at the start. We've got our masses here. And they have an angular velocity, theta dot 2. With a momentum, we'll assume it's pointing this way. And this is our angle 30. And then in our final position, it's going to turn, and go back to the same exact position again at 30 degrees. We're going to assume that the moment is pointing this way. This time, it has a different angular velocity. It's going to be equal to theta dot 1 at t is equal to 3 seconds. To be able to solve this question, we need to know the angular impulse momentum principle. So the angular impulse momentum principle is where the integral of the sum of moments with respect to time is going to be equal to delta h, so h naught 2 minus h naught 1, or angular momentum. If we rearrange that, we can get an equation that looks like this. And this basically means that the total angular impulse about a fixed point is equal to the corresponding change in angular momentum. So using this principle in our problem over here, we're going to assume that the moment is positive in this direction. And from there, we're going to take our sum of angular momentum minus the integral of the sum of moments. Here it's negative because we're assuming that our moment here is in the opposite direction. It's going to be equal to angular momentum in time 3. And then we're going to substitute in with our h02 and h03. So that's going to become 2md squared cosine squared theta multiplied by theta dot 2 minus the integral over moment. That's going to be equal to 2md squared cosine squared theta multiplied by theta dot 3. And for the average momentum, we're going to say that the average momentum is going to be equal to the integral of our sum of moments over the time difference between time 3 and time 2. So if we plug that into our equation over here, we get delta T m0 average is going to be equal to 2md squared cosine squared theta minus theta dot 2 minus theta dot 3. I just rearranged this over here. And then we're going to plug in our known values. To get a final answer of the average moment equals to 8.04 times 10 to the minus 3 newtons meters in this direction. Now for part C, we want to find the work done by the motor. So we're going to use conservation of energy equations. And since there's external work done by a motor, we know that the sum of kinetic energy plus work done by the motor is going to be equal to the sum of kinetic energy at 3. And then we're going to plug in our kinetic energy at 2, which is half mv2 squared, plus the work done is going to be equal to 2 multiplied by half mv3 squared. And if we rearrange that and sub in r theta instead of our velocities, we get d cosine theta multiplied by theta dot 3 squared minus d cosine theta multiplied by theta dot squared. We're going to simplify. And then we're going to plug in our known values. To get a final answer for work done equals to minus 0.0563 joules. For this question, we've got the motion of a rectangular plate P controlled by two lengths which cross without touching. So for the instant represented where the lengths are perpendicular to each other, where the lengths are perpendicular to each other, the plate has a counterclockwise angular velocity of 2 radians per second, and we want to determine the corresponding angular velocities of the two lengths. And the angular velocities are positive if it's counterclockwise, and it's negative if it's clockwise. So the angular velocities initially are 2 radians per second of the plate. And we've got the length of from A to O is 0.6, and the length from B to D is 0.5. Counterclockwise is positive. we want to find the angular velocities of the links AO and BD. So these links over here. First thing we're going to do is we're going to find the rotation about a fixed axis using vectors. So velocity is going to be the angular velocity crossed by the moment arm. AN is going to be omega crossed by omega multiplied by r. And the tangential acceleration is going to be alpha multiplied by r. So using these relations, we know that our VA is going to be equal to omega A with respect to O multiplied by RA with respect to O. VB is going to be similar. It's going to be omega B with respect to D multiplied by RB with respect to D, which means that using the relative motion, VA with respect to B is going to be equal to VA minus VB. So now we can rearrange this and plug in our VA and VB expressions to get omega AB multiplied by RAB is actually equal to omega AO multiplied by RAO minus omega BD multiplied by RBD. After we write this expression, we can plug in our known values. So we know that our omega P or our omega AB of the whole rectangle is equal to 2K multiplied by RAB, which is minus 0.3I plus 0.4J. This is not multiplied, by the way. This is cross product. So be careful not to confuse that with a multiplication. Equals to omega AO K cross product 0.6J minus omega BD K cross product 0.5I. We end up with minus 0.8I minus 0.6J equals to minus 0.6 omega AO I minus 0.5 omega BDJ. And if we simplify it even further, we get the relation of the angular velocity of link AO, which is 1.33 k radians per second. Because we've collected the I terms here, and we're going to do the same thing to find the angular velocity of link BD by collecting the like terms of J. And that's going to be 0.6J is equal to minus 0.5 omega BDJ to get a final answer of the angular velocity of link BD, which is 1.2 k radians per second. And for our last problem of this tutorial, we've got this figure that shows point B of a T-shaped bar with a velocity of 1 meters per second in the I direction and an acceleration of 2 meters per second squared in the I direction. So we want to determine the velocity of point D, and we also want to find the angular velocity of the T-shaped bar. So for this question, I'm actually going to flip the question. So I'm going to do question part B first, and then part A second. So for the velocity report of B, we know that it's equal to 1 meters per second in the I direction, and the acceleration is 2 meters per second squared in the I direction. We also know that the length AC and CB and CD are all equals to 1 meter. So part B asks us for the angular velocity of the T-shaped bar. And to do that, we're going to use our relative motion. So to find VA with respect to B, which is equal to VA minus VB. And then we're going to use the vector rotation and that's gonna substitute our velocity v with an angular velocity and cross product with r AB equals to VA minus 1I, because that's what VB is equal to. And then here I'm going to draw our A and our B, and we know that the distance between them is 2 meters since AC and CB are both equal to 1. So that must mean that the distance from A to 0 is equal to square root of 2, and from 0 to B is also equal to the square root of 2. This means that RAB is actually equal to square root of 2 negative I plus square root of 2J, and we're going to plug that in to our equation over here to get negative square root of 2 omega I plus square root of 2 omega j is equal to VAJ minus 1I. And if you notice here, VA is only in the j direction because as B moves in the I direction, A can only move in the j direction. There's no other possible way. So now that we've established that, we can collect the like terms of I and j. So we know that the negative square root of 2 omega I is going to be equal to negative 1I, which means that the angular velocity is going to be equal to 0.707 radians per second, counterclockwise. And now for part B, or actually for part A, we want to find the velocity of point D. So for VD, we're going to do the same thing. We're going to find the velocity of D with respect to B, which is VD minus B. Then we're going to substitute our velocity with the angular velocity, cross product the distance, RdB. And then we're going to draw our D and B position vectors. And we know that this is going to be equal to 1 meters, and this is going to be equal to 1 meters. So therefore, this has to be square root of 2, which means that the distance from D to B is going to be square root of 2 in the I direction. And we're going to plug it into our equation. And since we already know the angular velocity, which is the same as part B, we're going to plug that in. To get a final value of Vd equal to 0 meters per second. Thank you so much for watching this tutorial. If you have any questions about today's tutorial, you can shoot me an email at noor.dawidar@mail.tutorano.ca, or you can leave your question in the comment section below. Thank you and see you next week.